Hello, everyone. Thanks for joining me for the talk today. So my name is Juntao from Cornell University. So today I'm going to talk about our paper on multitask learning-based neural bridging reference resolution. And this work is in collaboration with Massimo Poisio. So let's first take a look what is a bridging reference. So a bridging reference is dealing with associative relationships between dimensions instead of the identity relationships that is normally dealing with coreference. So take a look at the example here. We can find the coreference links, the Bakersfield supermarket, the business, and it. And for the bridging, we have the customer, which is a customer of the Bakersfield supermarket. So there are a couple of challenges for the bridging reference. So the first challenge is different corpus follows a slightly different annotation scheme. So there are two major annotation scheme for the bridging, the definition of the bridging. The first one is the bridging based on the relational nouns. Such bridging relationships needs antecedent in order to be interpretable. Such as an example here, John walked towards the house. The door is open. So the door is associated to the house. And another bridging types is called it's more general bridgings. This kind of bridgings can be interpreted by itself, such as the example here. I went to Spain last year. I particularly like Madrid. So the Madrid itself is already interpretable. And the second challenge is data is very sparse. So we don't have much bridging reference in the corpus. Such as the largest corpus here we can find for the array IST only contains around 3K examples. All the other corpus are much smaller, such as the IceNode corpus only contains 600 examples. And as I mentioned before, the first challenge is a different annotation scheme. So the array annotated both types of the bridging, and the IceNode, Bash, and Science Corp only annotated the first types of the bridging reference. So in terms of the system architectures, so we adapted the state-of-the-art coreference systems, the Leota system. And the left-hand side, the left-hand part is basically the Leota system. The only exception is we replaced their Elmo embeddings with the BERT embeddings, as the later work shows that the BERT embedding improves the performance. And on the right-hand side, we use a multitask learning framework by training the bridging and the coreference together in order to improve the performance of the bridging reference to solve the problems due to the lack of the training data. And also by using a neural-based system, we naturally solve the problem of the different definitions of the bridgings, which basically we don't use any corpus-specific features in our system, and the system is purely trained on the training corpus. So whether the annotation is any types of the bridging, it doesn't matter for the neural-based system. So the first things we did is we trying to do a parameter tunings and see how we do how should we share the networks between the coreference and bridgings can achieve the best result. So the first things we did is we using our baseline system that trained only on the bridging reference. As we can see here, we first evaluated an antecedent selection task, which means that we use a gold bridging anaphoras, and the task is only trying to detect the antecedent for the anaphora. So for IST, we have already achieved a reasonably good result, which is 47.4. And for the IceNode, because the corpus is smaller, so we only achieved 33.8. By sharing the Elmo and the embedding and the LSTM layers, the system can achieve already a large improvement, and the improvement is larger for the ice node because the dataset is rather smaller. And if we further sharing additional layers of the feed-forward neural network, it can further improve the performance for both the IST and ice node coppers. And the best result is achieved by sharing one feed-forward neural network. So in total, the system has two feed-forward neural network, two hidden layers. And after we find the best configurations for the multitask learnings, we apply to a more complex task, which is full bridging resolution. So for the full bridging resolutions, we also tested on the IST and the ice node coppers. And as a byproduct, it will also have F1 scores for the anaphora recognition, because we don't use the gold anaphora anymore. So here we are trying to detect the anaphora, bridging anaphora as well. As we can see here, if we use only the bridging coppers alone, we can achieve only 30.8 or 30.5 for the ice node coppers for the full bridging, and also quite limited 20-ish for the anaphora recognition. And if we use the multitask learning approach by training it jointly with the reference together, we can largely improve both the full bridging F1 scores and anaphora recognition. But we still notice that the recall for the recall for the anaphora and the recall for the full bridging resolution is much lower than the precision. So which we suspect is mainly because of the coppers contains way more coreference examples than the bridging examples. So the bridging examples is a little bit underfitting. So we did some unsampling on the coreference part of the coppers. So we randomly filtered out some of the coppers from the coreference part of the training data. And then after we did those undersampling, the recalls for both anaphora recognition and full bridging were largely improved. As a result, the F1 score also improved. And after we got our best settings, we further analyzed on more coppers. We evaluated on 6 major bridging coppers. First, we tested on the antecedent selection task. As we can see here, our system is the only system reports the results for all 6 coppers, and yet achieved quite competitive result, the best result for 5 of them. The only exception is for the ice node. This is mainly because the whole system is mainly tailored for the ice node, and the performance drops if you apply the same systems to the coppers such as IST or the batch coppers. And in addition to the antecedent selection, we also evaluated on the 6 coppers for the full bridging and report to the byproduct, the anaphora recognition F1 scores as well. So the previous works from the Rosiger found that if they remove the gold coreference resolution anaphoras, the performance get improved. This does make sense because the task become easier if you remove the gold coreference anaphoras, and they only reported those results. So we also did the same procedure, follow their procedure, and to compare with their results. But we also report the result when keep the gold coreference anaphora. As we can see here, for all 6 different coppers, our system always outperforms the previous systems by quite large margins in all the cases. And as expected, our system is not its tolerance for the different coppers and the different domains are really robust to that, and achieved a relatively similar level result for all the different coppers. So if you are interested in our modules and the code is available, both the pre-trained modules and the code is available in my GitHub page. And thanks for joining us for my talk, and thanks for listening.